Problem 43 says that an urn, let's start here by drawing an urn, and in this urn there's 10 red, let's note that, we've got 10 reds and 15 whites, so 15 whites. So altogether there's 25 balls in here, and we're going to select the ball at random and not replace it. So what we're going to do is select the ball, not replace it, then select a second ball, and we want to show that getting a red on the second is just as likely as getting a red on the first. So show that the probability of drawing a red ball on the second is the same as the probability of getting a red ball on the first. So let's start here. What's the probability of getting a red on the first? Well, there's 25 balls in here altogether, and 10 of them are red. So this is going to be, well, if we divide by 5, we'll get 2/5, and you may know that to be 0.4. So the probability of a red on the first is 0.4. Now, let's find the probability of getting a red on the second. Now, here's a way to think about getting a red on the second. How could you get a red on the second? So I'm going to write this. I'm going to write red on the second in terms of everything that I've got in this urn. I'm going to do it like this. This is going to be the probability. Now I'm going to write a square bracket here. Here's how I could get a red on the second. I get a red on the first, and then I get a red on the second. That would do it. Or another way is to get a white on the first and then a red on the second, and close and close. Now, these two events are mutually exclusive because if I get a red on both draws at the same time, I can't be getting a white and a red. So because they're mutually exclusive, I can just add these probabilities. And this is going to be the probability of getting a red on the first and a red on the second. Add that to the probability of getting a white on the first and a red on the second. Now, this is going to be the first one, the probability of getting a red on the first times. Now, these events here are not independent, right? Because you're not replacing the first ball. So you're changing the sample space. So that's going to affect that second probability. So the probability of getting a red on the first times the probability of getting a red on the second, given that you got a red on the first. Plus, now let's move over here. This will be the probability of getting a white on the first times the probability of getting a red on the second, given that you got a white on the first. Now, I'm going to write these numbers up here at the top. I'm getting a little low down there. So the probability of getting a red on the first, well, there's 10 reds out of 25 balls, times the probability of a red on the second, given that we got a red on the first. Well, if we got a red on the first, there's only 9 reds left, and we did not replace that ball, so there's 24 balls left. Plus, now the probability of a white on the first, there's 15 whites and 25 balls altogether, times a red on the second. Now we didn't replace, so there's only 24 balls. A red on the second, given that we got a white on the first. Well, we got a white on the first, we didn't replace it, so there are still 10 reds. And when I multiplied these out and then added them together, I just happened to get 0.4. So now remember, this one here, this is the probability of getting a red on the second. And this one here, back over here, this is the probability of getting a red on the first. They're both equal to 0.4. So we've done it. Problem 45 tells us we have a bag. Let's draw our bag. And in this bag we have 4 blue marbles, 3 white ones, and 6 reds. So altogether, we have 13 marbles. And what's the probability? We're going to draw 3, all right? So we're going to draw 3. And the first part says this. What is the probability that they're all red? Okay, what's the probability that all are red? Well, to get all reds, now I want to write this. I want to write what I'm looking for in terms of everything that I've got in here. So the probability of all reds, what I want is I want 3 reds and 0 whites and 0 blues. And now I'm going to put this in our combination notation. So out of Now I want 3 reds. There's 6 to choose from. So 6, choose 3. Out of the 6 reds, choose 3. The whites, there's 3 whites. We don't want any of those, so choose 0 of them. And there's 4 blues. We don't want any of those either. So 4, choose 0. Now our denominator is the number of elements in the sample space, and there's 13 marbles in here. We're going to choose 3. And when I computed this, I got 0.0699. Now, the second part of the problem says, what is this? What's the probability they're all the same color? Well, we can get all the same color if we get this. Let's break this down into individuals. We can get all reds, or all whites, or all blues. Now I'm going to write these in terms of everything I've got up in here. But I notice first that I've got ORs. Now, ORs, are these mutually exclusive? Well, they are, because if I get all reds, I can't be looking at all whites or all blues at the same time. So they are mutually exclusive, so I know I'm going to be adding. So the ways I can get all reds, this is going to be, I'm going to use a square bracket here to bracket these off. To get all reds, I want 3 reds and 0 whites and 0 blues. Or, now I want all whites, so that would give me 3 whites and 0 reds and 0 blues. Or I want all blues, so I get 3 blues and 0 whites and 0 reds. Close and close. And now that I have it written this way, I can get the combination form. So out of those 6 reds, we want 3 of them. Out of the whites, there's 3 whites, we want 0 of them. And out of the 4 blues, we want 0 of these. Now this part right here, you recognize is just what we did back over here in the first part of the problem. But now, plus, right, and the plus comes from that OR. We now want 3 whites. So whites, there's 3 whites, we want to choose all 3. Reds, there's 6 reds, we don't want any of them, so 6 choose 0. There's 4 blues, we want 0 of those. Plus, now, we want all blues. There's 4 blues from which to choose, we want 3 of them. Whites, there's 3 whites, we want 0 of those. And there's 6 reds, we want 0 of those. And our denominator, once again, since we've got 13 marbles and we're choosing 3, is the number of ways we can choose 3 from 13. And when I computed this from round to 4 decimal places, I'm getting 0.0874. In problem 47, we're told that this fellow Horatio goes into a deli for sandwiches, and here's what he does. All right, maybe they get put in a bag, and he's got 2 roast beef and 2 hams, so altogether he ordered 4 sandwiches, and they're wrapped and put into a paper bag. There's our paper bag, and what's the probability that 2 sandwiches chosen at random? So R is equal to 2 here. We want to know if you just choose 2, both at random, we want the probability that they're both roast beef. So to get roast beef, here's what we would have to have. We would have to have, say, 2 roast beef and 0 ham. Well, we've got enough. We've gotten this form here. That's enough to make that computation. So what we have is this. Out of 2 roast beef, we want both of them. Out of the 2 hams, we want 0 of those. And our denominator is, out of the 4 sandwiches, we want to choose 2. When I computed that, I got 1/6, or 0.1, and then 666. I'm going to round to 4 places. I'll get a 7 there. The second part of the problem says, what's the probability that they are both alike? So I'll write it in English first, and then I will try to make this look like what I've got in here. So both alike must mean this, that they're either both roast beef, which we just found, or that they're both ham. So again, I'm going to get these in terms of everything I've got in here. So to get both roast beef, this is going to be the probability. I'll use the square bracket here. We want 2 roast beefs and 0 hams, or we want 2 hams and 0 roast beef. Close and close. So let's count. There are 2 roast beefs from which to choose. We want both of those. There's 2 hams. We don't want any of those. Or, now there's 2 hams. We want both of those. And there's 2 roast beefs. We don't want any of those. And then our denominator, once again, is out of 4 sandwiches, choose 2. So this one just turns out to be, actually, do you see it? It's just going to be double this one right here, which turns out to be 1/3, or we can just write 0.3333.